shift. I was like, no, I can't do both of you. Okay, there.
We're in the Pythagorean theorem section 4.1. What kinds of homework questions do you have? Yes. Section 4.1? No, 3.3?
4.1, but I'll just check. 15.
4.1, number 15. Oh, the train track problem. I thought this was very interesting. Train tracks are made of metal. Consequently, they expand when it's warm and shrink when it's cold. When riding in a train, you hear the clickety-clack of the wheels going over small gaps left in the track to allow for this expansion. Suppose you were a beginner at laying railroad tracks and forgot to put in the gaps. Instead, you made a track 1 mile long that was firmly fixed at each end. On a hot day, suppose the track expanded by A equals 4 feet and therefore buckled up in the middle, creating a triangle. So here's the track when it's cool, all nice and flat, but then it gets hot and the track goes up in the middle. So now the track is 1 mile and 4 feet. Let's go ahead and check out how tall this would be, okay, if it all buckled up in one spot. You actually see this in real life, not on train tracks, but on people's siding. You ever see someone do siding on a house and it's all buckled and falling off? That's because they forgot the expansion joints usually. Let's go ahead and take a look here for this track, for this particular problem. So mine's going to be a little different than yours possibly, depending on your numbers. But here's how we do it. So the length is 1 mile plus 4 feet now. So you need to know that 1 mile is how many feet? Who looked that up? 5,280. I heard it, did not see who said it. So now this length is 5,280 plus 4. So 5,284 feet. Meanwhile, on the bottom is still 5,280. Now we're going to divide it in the middle. So when we divide it in the middle, we get a right triangle. But now there's only half as much track above and on the road bed below where the track used to be. So take 5,284 divided by 2. So 2,642 and 5,280 divided by 2. 2,640. And we're trying to find x. So what we've done now is made a right triangle. So lots of problems in life can be split up into, lots of geometrical problems can be split up into pieces that form right triangles. And that's nice because if you know two sides, you can find the third side. So the hypotenuse is the 2,642. We'll go ahead and square 2,642 and square 2,640 and then subtract this. What did that come out to? 6,969,600 from both sides of the equation. So it's 10,564 for b squared, and then we just take the square root of both sides. So mine is 102.78. So that's quite a buckle on your bridge there. Anybody have any questions? Any other homework questions? Okay. We were in section 4.1 looking at the Pythagorean theorem. The life lesson in that section is to experience ideas in as many ways as possible. So we're looking at several proofs of the Pythagorean theorem, and hopefully one of them clicks for you and you can understand it well. So that would be the one that you'd want to practice, right? So remember, proofs on quizzes are some of the higher point value questions, so you want to make sure you understand your proof well for your quiz so that you can get the most points you can. So this would be something I would expect you would practice every week till the quiz to make sure you can do a good job at it. Well, our third proof actually starts with the c squared that we had assembled last class. So we were looking at the Pythagorean theorem, and we were looking at a squared as a square a by a, b squared as a square b by b, and so on. Because that is how the ancients would have looked at a squared, b squared, and c squared. We had assembled then a square that was c by c, so that's what we're going to do again. If you need to borrow scissors, if you have the template but they haven't cut it out, I have a couple pairs of scissors up here you can get and use. I'm going to try and fit the c squared and the drawing on one screen. I think I can do it. Let's see how it goes. So we're making a square c wide and c tall. Now as you're doing this, you're making a square, and the reason you're forming 90-degree angles is because on your right triangles, when you take away the right angle, the two angles that are left add to 90 degrees, and you can verify that when you put one of your templates over those two angles together and see that they form a 90-degree angle. So we're getting the c's on the outside, that leaves an empty square in the middle, but we figured out the size of that square, right? The size of that square, you take the long leg A and subtract the short leg B, and that gives you the size of the square, A minus B on each side. Well, let's go ahead and draw that, because proof 3 begins with this drawing that we've already looked at once before. So when we sketched it last time on graph paper, we made it 8 by 8, and I think that worked fairly nicely. So let's go ahead and do that again. So use your straight edge and draw 8 by 8 square. So we're just making a square, and we're copying into the square the shape that we've made with the Pythagorean cutouts. I'm making mine 8 by 8 if you would like to match, or you can make a different size. So once you have your square sketch, then you use your straight edge to make the triangles. So lay your straight edge so that it has one side passing through one corner and one through another. So now my ruler is acting like the red square right here. and I'll just outline it. So I have the red triangle started, and now I'll put the green one in. So let your square corners go through the two sides of your straight edge. So we're getting there. Now once you have that sketched, it's important to label it, because your sketch won't be perfect. It might be very nice, but it's still not perfect. And by your labeling it, you're showing that each side that's labeled A is supposed to be the same length, even if your drawing is off a little bit. And that when you put the little square corners in, you're making right triangles. So put your right corners in, your right angles. This is one of the oh, well, not yet, never mind. So put your right angles in, and then your C's were the hypotenuse, and your A and your B. Your A was the longer leg, and the B was the shorter leg. So even if my lengths aren't perfect, by labeling them, I'm showing that these are the same size. They're supposed to be the same size. It's important to label your square on the inside as well. Okay, so we'll label that. You can see its length is the long length A minus the short length B. So A minus B per side. This is the proof that takes the least amount of algebra. We're going to just say this is C squared, because it's a square, C on width and C on height. So that's why it's C squared. It's C wide and C tall. So length times width is C times C, or C squared. But what we're going to do is we're going to come up with a way to take these same shapes, okay? We're going to use exactly the shapes here and use all the shapes up to make them fit A squared plus B squared. So we're going to rearrange these now, these pieces, to make them into a shape A squared plus B squared. Now A squared will be a square A by A, and B squared will be a shape B by B, and you want those at the same time. So you can't really separate out the A squared and the B squared. They're going to be attached. So you're going to end up with two squares that are attached. One square will be size A by A, and one will be B by B. So this is a puzzle. You rearrange the pieces until you find those shapes. So go ahead and use your shapes and manipulate them. Once you have the shape A squared plus B squared, we're going to take a picture of it, and that's what you're going to put in the Dropbox. So hopefully you can figure it out, and I'll come around and help you. Okay? So you're trying to arrange those into shapes. It's a puzzle. You're trying to make a square A by A, and it will be attached to a square B by B. Anybody else need a scissors?
No, that's B by A. You have like two shapes. Did you put yours together? Because you have like
More shape for me. Oh no, this is like extra stuff.
Yeah.
Extra stuff. You have 2 rectangles, so that's good. That's good.
Oh, is it?
Yeah, well, that's a good start. Now you have to shape them somehow so that they form 2 squares, and you'll need your little square as well. Yeah, so include your square in there. They're all like top triangles. All your pieces need to be used because that's how we'll show that c squared is a squared plus b squared, because we'll use the same figures and use them all up. So the same area, just rearranged. Do you want a scissors? Oh, yeah. Who's done with their scissors? So that's good. I see you making rectangles, and I see you rearranging. That's good. Think about it. If you have a square that's B wide and B tall, and a square that's A wide and A tall, and you put those next to each other, what shape do the 2 squares next to each other make? Your author calls it a fat L shape, right? Because you put one big fat square next to a smaller square. So that's going to make a fat L. So as you're trying to rearrange and make this puzzle that I haven't given you the picture for yet, it's going to need to come out like a fat L. Yeah, that's a fat L shape. It's a different kind of L. No, you have 2 different kinds of fat L's. Yeah. So you have 2 different ones. So you have to figure out which one, or maybe, I don't think this one quite fits in there.
Rather than no.
Yeah. Okay. So now that's the right idea, but it's not quite there because it's not making that a squared and a b squared, but you have the right idea going. So a lot of you are beginning with your 2 triangles making 2 triangles making a rectangle, and the other 2 triangles making a rectangle. That's good. Okay, so that's very good. So your 2 triangles make one rectangle, 2 triangles make another rectangle. Those are good to work with when you're trying to make a fat L shape. And I see somebody got it. Yay! Okay, I'll show you what you do. So you have these two rectangles. So that makes an L, but we haven't used this last piece yet. So we'll put it right here. I wonder if it looks better without the light on. Let's try that. Unless we can't turn the light off. Okay. The light is going to stay on. So you have 2 squares, right? You have a square above and a square below. I'll put a ruler, a marker here to delineate the 2 squares. There. So now you can see you have a square above and a smaller square below. So let's check out the areas of these 2 squares. So the c squared, it was pretty easy. You had c wide and c tall. Looking at the square that's above the black marker, what is the width and height of the square above the black marker? Yes.
Minus b. So
we got the whole length. Okay, so it's,
although the entire, oh,
yeah.
no, no, B plus
Mhm.
B. Or, I can't read that.
Yeah. That's true, it's tiny. Here, I'll see if I can make it bigger.
What is it? Oh, A, okay, A minus B plus B.
Yeah, so that's how wide across it is.
A plus B.
And actually that's shown up here as well, right? So you have your A up here on the orange triangle, and that's the same length as A minus B plus B, which makes sense if you do it algebraically. A minus B plus B, that's a B. I mean, that's an A as well. So either way, you can see how wide it is. It's A wide, and that A can be expressed as A minus B plus B here. And that's a nice thing because then you can see it vertically. So the vertical length is B plus A minus B, which is A again. So it's A across the top for width and A tall when you take the B from the small leg here and add the blue square's length, A minus B, and you get A. So A by A squared. There's your A squared. And now looking below the marker, what is the dimension there of that square below the marker? Well, how wide is it? How wide is that square? You see my tiny little writing? It's B. Yeah, it's B wide. So it's B wide, and the height is also B. That's a little harder to see, but if you take the whole height of the red triangle and you take away the blue square, that leaves B. So I'll just show you that by taking this one and borrowing it there. Okay, so you take away B from the height of the red triangle. I'm sorry, I said that. Yeah, you take away the blue square from the height of the red triangle, and it leaves the orange base. So orange base is B tall. So below the marker we have B wide and B tall. You could do that algebraically as well. You could think of the height you're trying to get here as A minus the blue square. So it'd be A minus B, and that becomes positive B when you subtract. Okay, so take a picture of that, and that would be what you upload to the Dropbox for 4.1. That's the fat L shape. And then we're going to go ahead and draw it because you'll want it sketched in your notes. Do not use my sketch. Do not take my picture. Okay, you need your own picture. If you take a picture from the overhead screen, that won't count. Okay, I'm not going to give you credit for that. Yes?
Do we have to have the square in there too?
You need to have the square in there too. Yep. Because that square means that you're using all of the shapes you used over here to form C squared. And when you use all of those shapes, then you get the whole A squared plus B squared. And that's why we're able to say that the C squared equals A squared plus B squared. So we'll transfer the drawing over there after you get a chance to take your photo. Let me get my big fat marker. I like it right stuck there. Okay, so we're going to transfer this drawing. So I'll make it a little smaller for a minute. I'm not going to try and draw it to scale with the other one, and that's again why we label the A, B's, and C's, because then it shows that even though we're not trying to draw it to scale, the C on the left is supposed to be the same size as the C on the right. In fact, let's sketch these to fit the 3x5 index cards that we're using. So let's make rectangles that are 3x5, and then draw the diagonal down them. So 3x5 for a rectangle here. So we took a 3x5 card and cut it on the diagonal, and that's what we're doing with our little squares. So now we need a 3x5 rectangle coming down from that. And last, you need the little blue square. To draw it to fit with these, it would be 2 units by 2 units, because it's B minus A. It's 5 minus 3, or 2 on our drawing. But of course, we're not going to label it 2. We're going to label these A, B, and C for lengths, and A minus B. Because this is true not just for the triangles that we're using, it's true for any right triangles. And so if we put A, B, and C down, then it's generic to fit any right triangle. So I'll blow it up now. Kaboom. No, just kidding. Okay. So here's our hypotenuse C, our right triangles, so put little corners in. And then we made the long legs A and the short legs B. And then that little square was A minus B by A minus B. Now you have to show that you know this makes up A squared and B squared. So once you have your drawing, you need to take a different color and separate the two squares with a dotted line or some other notation, okay? So above the dotted line, we have a square A by A, which is A squared. And below the dotted line, we have a square B by B, which is B squared. So this proof is the least algebraic of all the proofs that we did. So if you're more into geometry than algebra, this might be the proof that works for you. I sometimes think, well, I maybe don't have to look at all 3 proofs. Maybe everybody really likes a particular one, but when I give the quiz and let people pick the proof, that's pretty much distributed amongst all 3 proofs. Does anybody have any questions? Okay, if you didn't have your cutouts with you and you want to take a picture of your drawing like this, you could do that as well for your upload, okay? Let's go on to the next section then. In the next section, we're looking at art galleries. The next section is 4.2. And we start with a strangely drawn art gallery. Here's a floor plan for an art gallery. If you stand in the corner marked A, which walls or parts of walls can you see? What if you stood in the corner marked B? How many guards would you need, each standing at a corner, so that each wall could be seen by at least one of the guards? So the guards can turn their heads, but they cannot leave their corners. So how many of you have been to an art gallery? Anybody else ever been to an art gallery? My daughter was an art major here. I went to lots of art galleries here. That's actually a very hard major. Are any of you art majors? I had no idea how hard it is. You've got a lot of hours you got to put in. Like, they tell you, don't just draw one picture, draw 15 pictures. Don't make one bowl, make 15 bowls. Oh, now you need 15 vases. You know, it's a lot of hours you put in. Okay. So, anyway, if you go to an art gallery, who thinks you need guards at an art gallery? Yeah, definitely. Yeah, especially in Europe, a lot of the art is in private collections, and the people open their homes to make money so they can support their private collections, and it's hard not to be assured that somebody doesn't walk off with something. Well, this is a question posed in 1973 about how many guards are needed in an art gallery. So that's the question we're exploring here. So let's take a look. Where would the guy standing at A be able to see? Where would that guard be able to see? Well, the guard can't see through walls. So the guard can see, yes, do you have that?
Like the line of vision of that
Yep.
triangle, everything. But that was a triangle, everything.
Exactly.
Field of view.
So the guard can see straight lines until the guard runs into his sight runs into a wall. So think about B. Now the guard can turn their head 360 degrees. They can't leave their position though. So think about B and think about where the guard at B would be able to see. Okay, so here's your guard at B. Could your guard at B see everything inside of this pointy area? So the guard's, I put the B out here, but really the guard's supposed to be on the inside of the wall, not the outside. So the guard is right here. The guard can see everything up here, okay? He can see everything in this point. How much of this rectangle can the guard see? This rectangle down below.
Can't you see all of it?
Yeah, the guard could see the whole thing because the guard's standing right here. You can look to this side, you can look to that side. Can the guard see up in this area? No. The guard cannot see up in this area. Can the guard see over in this area? No. Okay. Now I want you to think about the least number of guards that would be necessary to see all the inside walls. When you think you know, then you tell me, okay?
2.
2. Okay, so where would you put them if there were 2?
The bottom corners.
Okay, so the bottom corners. So the one down here could see all the way up in there, and it could see all this area, but couldn't see all the way up in here because if you do a straight line, it could only go up to there. Okay, so the guard could see almost that middle room. How about the other one? The other guard at this corner couldn't see quite, so they couldn't get quite in the tip. Okay, so we could either add another guard, so there's 3 guards, or we could think again, did anybody find another way that 2 guards might work? Yes?
Put the 2 on the bottom, so half and half.
Oh, they got to be at the
Not
corners.
there, but on the corners, but in like halfway.
Oh, yeah. Is that what you were thinking too, maybe? Yeah. So like right here. Okay, so in our problem, the guards have to be on the corners, but that's an idea I hadn't thought of that. So yeah, that would probably actually work, and that maybe would be what you were thinking too. So if our guards got to be at the corners, are we stuck with 3 guards? I think so. I didn't see another way. Well, we're going to be looking at particular types of art galleries here, so let's go ahead and draw what kind we're going to be looking at. So in 4.2 we're looking, well, let's see the different kinds of art galleries we could consider. So these are supposed to be straight lines. So So here's kind of a C-shaped art gallery with kind of a door going on. And here's another floor plan. This floor plan has a courtyard, so there's a nice big cutout in the middle. The next one is kind of a starburst kabam kind of thing going on. So that's kind of a weird shape. And last we'll look at one I think is the most normal shape. So we'll put a rectangle with some interior walls. I like that one the best. Well, it turns out that the art galleries that we're going to be looking at are all what are called polygonal closed curves. So the only one that's a polygonal closed curve here is the one that looks kind of like a starburst. So a polygonal closed curve is a figure made up of straight lines straight line pieces, not straight lines. Straight line pieces that are connected end to end. That are connected end to end to form a loop. So polygonal closed curves are figures made up of straight line pieces that are connected end to end to form a loop. So can you tell me why the first figure is not a polygonal closed curve? Why is this not a polygonal closed curve? It's that close, yeah. There's a little opening, presumably a door. How about the second figure? Why is the second figure not a polygonal closed curve? How does it fail the definition? Always go back to your definition.
Because all the lines aren't connected, the lines don't meet.
Yeah, the lines aren't connected. They don't meet. Yep. Okay. That one is a polygonal closed curve. Those lines are supposed to be straight. They are not quite straight. Okay. How about this figure? Why is this not a polygonal closed curve? Yeah, they don't connect together. That's right. Okay. Well, what I'd like you to do is to draw a polygonal closed figure at your desk, and then figure out the least number of guards that need to keep watch in there, and also count the vertices. So to count the vertices, we count all the corners. So the vertices here, I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I already counted that one, so 10. So count the vertices and figure out the least number of guards that you could have. And once you've done that, write it down and then pass it to the neighbor and trade and check each other's work. And I'm going to come around and gather that data after you've checked each other's work. And I'll come around and help you if you get stuck. So draw a polygonal closed curve. Count the vertices. Okay, so those are the corners. They're going to call it N. And the smallest number of guards to see the whole thing. So once you have yours done, go ahead and Yeah, go ahead and trade with the neighbor. Trade with your neighbor.
Are you done? Yeah. You did how many races? And Golden Dora. Can you check each other's? Okay, trade and check. Trade and check. 1, 2.
Good diamond. No way. I did, okay, then I did diamond and arrow.
How many cards? Just really good check.
I'm gonna take one.
Just check each other's.
Is that what we?
Yeah. You gotta hand these over, sure.
There's my bigger star.
Yes, you. Okay, so you two, can you please, can you check with you and check with you? If there's 3 of you, you can check, you know, in a circle kind of thing, okay? So in the back row here, could you please, do check, could you check? Oh, wow, okay, so then it'll be this way. Yeah, what did you find? Okay, did you check each other's then?
Yeah.
What was your score?
Because like she doesn't like clear and then
I forgot. 6, 10, 2. Okay, did you two check each other? Yeah. Okay, what is
I
your
don't know
score?
what other I still cried at the end. But I was always anticipating certain things, like when he was gonna
Yeah, right.
You're what? I still cried at the end.
Here.
Yes. Did you two check each other? What did you guys?
I just got
No.
How many verses?
Same,
I know. I'm working.
Or just 7, 8.
Okay. 10 and 4? I think you can do it with less.
Really?
Yeah. 4 of us.
Maybe have like
Yeah, you can. Okay. So what was it then? 10 and 3? Yeah.
I have a.
Did you check with somebody? Did you check? Did you check on him?
Yeah, originally my best friend had cancer, the scene where she made using some
Oh, so you made like.
literally that easy. So that those were
Ten and 1.
This one's 12.
she's like, I know my friend would like to and then those were like audience, so she was like, my friend has passed through cancer,
What did you have?
so just keep in mind somebody that's close to you. And that's why I know about emotion we have.
Okay, 6 and 2. That one was actually.
And then she was emotional when she was going through where she already knew that he died.
Yeah.
So that was hard. I really like that part.
No, that's what I'm looking at right now.
The original movie that passed our daughter remakes was like about Hollywood stars. 1930s. It was like the very first, it was like, so it was the first movie where it was like mainly an actor and an actress, and then there was a remake called Stars Born, and then the remake,
So I was like,
I think I was there. I read that. I thought it was the original story.
Right, and again.
your exams are really hard. Like,
Did you all check on
like
yours?
long ass answers.
And there's
There is, yeah, I should remember. See, her style is used
Okay, I gathered all the data. There was some very interesting and some very simple, which is good too. Now we're going to add one more column. That didn't fit. I'll fold this down. Then it'll fit. Now we're going to put one more column, and the column is n over 3. So the number of vertices divided by 3 from your examples. So 4 divided by 3 is 1 point something. 3 divided by 3 is 1. 6 divided by 3 is 2. 4 divided by 3 is 1 point something. 8 divided by 3 is 2 point something. 6 divided by 3 is 2. 10 divided by 3 is 3 point something. 12 divided by 3 is 4. No idea what that is. I think it's an 8. 8 divided by 3 is 2 point something. 12 divided by 3 is 4. 9 divided by 3 is 3. So I took the first column, the number of corners, and divided by 3, and got the second column. So, because now I'm going to ask you about it. I'm going to say, what do you notice about the second column and the third column? What do the second column and the third column? A lot of them match. Let's see which ones match. This one, this one, this one, this one, this one. Okay, so the ones that don't match, what can you say about the two columns? So comparing the numbers in the two columns for the ones that don't match. Which ones are bigger? The third column. The third column is bigger. Either they're matching or the third column is bigger. That is actually the basis of the art gallery theorem that we're going to write out. So the art gallery theorem actually is a theorem. It was proposed in 1973 and proven shortly thereafter. The art gallery theorem says, suppose we have a polygonal closed curve in the plane. Suppose we have a polygonal closed curve in the plane with V vertices. So V vertices. Then there are V divided by 3. Then there are V divided by 3 vertices. From which it is possible to view every point I was thinking about proofs, so I wrote the wrong word. From which it is possible to view every point. to view every point on the interior of the curve. To view every point on the interior of the curve. If v divided by 3 is not an integer, if v divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v divided by 3. The biggest integer less than v divided by 3. We are able to see every point inside from less than or equal to v divided by 3 vertices. So from the beginning, suppose we have a polygonal closed curve in the plane with v vertices. Then there are v divided by 3 vertices from which it is possible to view every point in the interior of the curve. If v divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v divided by 3. We are able to see every point inside from less than or equal to v divided by 3 vertices. So in Friday's class, we'll go ahead and see, well, why is that possible? Why can you always, no matter how complicated this polygonal closed curve is, station guards at v divided by 3 of the vertices? I'll see you on Friday. Yes, but I'm going to make it a little smaller.